Hello everyone and welcome back to this episode of the Funtastic Academy. In this episode, we'll continue from where we left off last time and talk about the floating point standard. Last episode, we mostly covered in rough terms how the floating point standard saves space and allows you to represent numbers with a high degree of both precision and magnitude. In this episode, we'll get into the nitty-gritty details, discussing how every single bit in the standard works to represent a number. Now, before we can continue, we have to address the elephant in the room. I'm talking, of course, about last episode's quiz question. Last episode's quiz question was, drumroll please, what is the name of the IEEE standard that discusses the floating point implementation? And the answer is the 754 IEEE standard. IEEE 754 is mostly considered with describing the operations and things that the floating point standard should be able to do. But it also discusses how each bit in each of the floating points variations work, as well as the subnormals, infinity, and other minutiae of the standard. Without out of the way, let's hand over the mic to Computer Ayush and dive in.
Thanks for that, Ayush. Now back to me, Computer Ayush, with the spreadsheet from last video. Now, in last video, we discussed how just normal signed integers are pretty unsuitable for representing large numbers. We took the example of an account system where because we are only representing changes of money as small as $8 in a system with tens of billions, we had to add extra bits, wasting a lot of memory space. So in this video, we'll cover the Exponent and Mantissa systems and roughly see how the floating point standard solves this issue. Now, let's just, for demonstrational purposes, try to replicate how this type of system would work using the decimal number system, which you're familiar with, make it much more simple. So let's say that instead of having 32 bits, binary digits, we instead want to represent a number with just 4 decimal digits. How would we do that? Well, the logical solution, which is what signed-ins use, is just use 4 digits representing the value of the number. So we would have 4 digits like this, 0000, ranging all the way up to 9999, or just shy of 10,000. Now, we have a very high precision for all the numbers we have. It can tell the difference between numbers like 10,000 and 10,000 minus 1. The flip side of the coin is it can't tell the difference between 0 and 0.5. It has the same precision for all the numbers we have. Each number has a gap of 1 between them. But when I talk about very large numbers, I can afford to be a bit less precise, which is what we covered in the last episode example with the account system. What's the solution to this problem? Well, floating point solves this with a system of scientific notation. So the concept is we would just have 3 bits as a mantissa, and we would multiply that by 10 to the power of an exponent bit. So the advantage of this type of system is we can represent huge numbers. Let's say I maxed out all the digits again to the 9. By the way, the 10 that we have over here, it's part of the standard because we're using decimal. 10 to the 9 is 1 billion. So we're representing just shy of 10 billion here. Not bad. That's way bigger than the 10,000 we had before. And it can represent really small numbers too. The smallest number that this can represent that isn't 0 is 0.01 times 10 to the 0, or just 0.01. 10 to the 0 is just 1. So it can represent small numbers that are less than 1 with really high levels of precision, 2 digits, and yet it can still represent massive numbers. But one drawback to the system is that when you're dealing with these massive numbers, there's a loss of absolute precision. So let's say I have over here just shy of 10 billion. Let's say I wanted to choose the next lowest number. Well, that would be 9.98 times 10 to the 9. That's the next lowest number that we can choose. But this is lower than the previous one by a factor of 10 million. Now you might think that that's a huge precision loss. Why would I want numbers 10 million apart? And the answer to that is pretty much when my money is in the tens of billions, measuring differences on the scale of millions really doesn't matter that much. So this is essentially how floating point works, with this mantissa bit representing the absolute digits of the number, and then this exponent representing approximately the total ballpark of the size of the number. Now, we need to make two adjustments to make this fully conform to the floating point standard. The first edit that we'd like to make is allowing for negative exponents, which allow us to represent small numbers with much greater precision. So let's say that instead of having this exponent bit range from 0 to positive 9, we let it range from negative 4 to positive 5. Now the disadvantage is that the maximum number we can represent is much smaller. This number is now equal to just shy of a million, which is still huge, but it's much less than the 10 billion that we had earlier. But now we can represent small numbers with a huge degree of ease. This is now the smallest number we have, which is 1 over 100 times 1 over 10,000, which is 1 millionth. That's a huge degree of precision for these small numbers. And that allows a huge degree of accuracy for these small computations. And this negative exponent bias is basically what the floating point standard use. We can see that we have in the exponent column, these green bits are the exponent. Logically, these range from 0 to 255, but they are biased. They range from minus 127 to positive 128. So if I wanted my exponent to be equal to 0, I will actually have to set it to positive 127 to make it equal to 0 here. I've made quite a comfortable user interface for you to easily see all the parameters we're changing. Now the second edit that we'd like to make is really a nice trick we can do in binary so that we can actually get an extra 33rd bit for free. But to explain it, it's a bit complicated. This is how, with the current decimal floating point we had, we'll represent the number 12. 1.2 times 10 to the power 1, 1.2 times 10, 12. But the thing is, we could also just as easily do something like this. 0.12 times 10 to the 2, 0.12 times 100, 12. Both of these numbers are completely valid with the system we have. So the issue is we are wasting a number. Both these spaces are pointing to the same thing when one of them could be different. With decimal, we have no solution but just simply call this invalid. But with binary, we can actually pull off this really neat trick. Now, reason that a number like 1.20 times 10 to the 1 is valid in a decimal system but not 0.12 example is because it starts with a non-zero digit. We could always just reduce the number by just adding a 0 in front and then just increasing this exponent. But we can declare that's invalid and just say that every number must start with a non-zero digit. The exception for this is of course 0 and very small numbers close to 0, which of course have to start with a 0. We'll deal with numbers like these called subnormals in the next episode. But the thing is that in binary, the only two digits we have are 0 and 1. So non-zero digit just means 1. So as long as we don't happen to be representing 0, we can essentially have to guarantee that there is a 1 right in front of the mantissa. But if there's going to be a 1 anyways, why represent it? We can just put it in this little magical box we have here and just tell the format to imagine that it's really there. And this is why our mantissa is coming out as 1, even though it's just all zeros. We are inserting a magical 1 point right in front of it. So let's use this with a practical example. Let's say I wanted to represent a number like 1.25. Well, we already set the exponent to the power 0 or 1. So now with the mantissa bits, I just have to put 1.25. We already have the 1, so we need to add the 0.25. If this has a value of 1, this will have a value of 0.5, this will have a value of 0.25. We can just set that to 1, and there we go, 1.25. Here's another example. Let's say I wanted to double the number we have. Well, I can't just simply move this to a left and increase this because we still have this magic 1. So I'll have to change all these bits to 0. So we'll have 2 to the power, the higher exponent, 2 to the power 1 times 1.25 in a mantissa. 2 times 1.25 will be equal to hopefully 2.5. And if we see our result, we can see we did in fact get 2.5. The mantissa is unchanged, it's still 1.25, but we're multiplying it by 2 to the 1, giving us 2.5. And there we go, that's the rough basics of the floating point system explained. To summarize, we have this blue sign bit that determines whether the number that we're expressing is positive or negative. These 8 exponent bits are biased. We have this magical 1 here to save us an extra bit, and these mantissa bits which really hold the digits of the number. And that's how floating point can represent numbers across vast scales of magnitude with a very high precision. Now, back to Canva, Ayush.
Thanks for that, Computer Ayush. So, let's recap what we did. In summary, we learned how the sign bit, 8 exponent bits, and 23 mantissa bits work together to represent a floating point number. We also covered how you can represent a demonstration number in the floating point standard using things like the mystery first 1 bit in the mantissa that's missing, as well as handling the exponent bias and sign bit. So, before I'll leave you with a quiz question. This should be easy to answer for anyone who's been keeping up with this video. What is the bias that is added to the exponent in order to represent negative exponents in the binary 32 floating point format? Tell me the answer and I'll see you in the next episode of the Funtastic Academy. Bye!